Guys, I hope that I am audible to you guys. In last lectures, we discussed about the basics of control. I discussed it because I wanted to implement the controls and wanted to show how we can implement the control in Matlab. So today, we're going to simulate a process, and then we will try to find out the dynamics of the system, and then we try to control it, let's say, using some of the manipulated variables with p controller. So here is the system. I don't want to go exactly in details of the system, but let's consider there is a biological reactor modeled using following differential equations. So there are three differential equations, that is dx by dt, ds by dt, and dp by dt. These are the three differential equations with initial conditions at x of 0 is 6, s of 0 is 5, and p of 0 is 19.4. So these three differential equation basically constitutes a model for biological reactor. Then question is, we can first find out the steady state values and then plot the state variables, that is x, s, and p with time. And then we will give step change in mu m and report the steady state value. And then with the same system, we might go and implement a controller. Okay. So I wanted to show you how we can proceed to develop a controller for any system. So if you modeled any another system, you might end up with more than three differential equations, 10 equations, 15 equations, or a set of algebraic and differential equations, so and so forth. But the methodology looks similar. Okay. So I am going to perform this step by step. So you follow me and do the same thing in your systems also. So here I open a Matlab. I changed my folder and path to where the folders I wanted to save. And then I'm going to write first a script file. Okay. Now look at the differential equations. Let's say we define time space at this point of time 0 to 10. So I have t span as 0 to 10. We will see later on, we can refine it. Then I am going to define all these variables. That's alpha 1, then alpha 2 pf, k1 d mu m, k1 d mu underscore m, km and sf, km and sf. I'm going to write the values of this 2.2.2, 0.2, 0.2, 50, 0.0045, 50, 0.0045, 0.45, 0.00, 0.48, 1.2, 0.48, 1.2, and 20. So I defined all variables. Now I need these if you look at the differential equations, I need these variables inside the function file. So I can bundle it so that it's easy for me to supply. So I say data underscore p, which is parameters, is equal to alpha 1, alpha 2, so I created data p. Then I have initial condition for which I'm going to write by x0 as 6519.14. 6519.14. The road initial conditions, I will call the differential equation here as t comma y equal to 45 at the rate of, let's say, the functions biological reactors. Then I think I had to give initial condition a t square. So I have t as span, then I have initial conditions, then I need to give empty brackets, and then I need to supply data underscore p. What I'm going to do, I'm going to wait here for maybe 2 minutes.
Hello, sir.
Yes.
Sir, why do we give those empty brackets here?
Actually, in syntax of ODE 4.5, first is a functions which we call, second is time span, third is initial condition. So this is perfectly fine. Okay.
Yes,
Now
sir.
the fourth slot they given for options. So for example, there is a maximum tolerance we can set, relative tolerance we can set, maximum number of iteration we can set. Okay.
Uh,
So that you can see as a help ODE set.
so
Okay.
after giving these empty brackets, I can give n number of parameters.
Yes, you can after that option slot, there is a one more slot by which you can supply the parameters.
Okay. So if
So
at
let's
all
assume that, yeah,
after
sorry.
data p, I am required to give another value k. So I can give comma k.
Yes,
Okay.
but I right now here I am bundled everything, so it's
Yes, sir.
easier for me. Correct.
Yes, yes.
Okay. So I'm going to wait here for 2 minutes. You can maybe type it down. so that you are also going to develop the file. I am going to just taken one examples for developing the controller. So follow me.
Excuse me, sir.
Yeah.
Sir, in second equation, ds by dt is equal to, sir, what is the value of capital Y in there in second equation?
Why not given? Assume as a 5. Let's see what happens. You can assume as 5.
Okay, sir.
Yeah. So we wrote the script file. Let's write the function. We have functions. Then we have output as dcdt. Then we have function file name, which we can take it from here. Function file, input argument t, output arguments, let's say y here I will take, then the data underscore r. That's the third slots. Okay. Then first what I am going to do, I'm going to unbundle the data which I wrote here. So I know that alpha 1, alpha 2, here A1, B, BM, yeah. And he suggested that there is a y also, so I'm going to take y, capital Y inside this, and I'm going to write y is equal to 5. At this point, I really don't know. So here I came and wrote y. So I know that the first element of data underscore r is alpha 1. Then 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are the parameters I taken in my function 5. Now I know that there are three differential equations. So I can write dc dt is equal to ZROH 3 comma 1. This will know that MATLAB will know that there are three differential equations. Okay. Now let's try to code the differential equation first. So I have dc dt of 1 is equal to. So mu dx, x is the state variable. So I can write mu minus d into y of 1. Correct? Because my first differential equation is x. So this becomes the x elements y1. Second dcs dt, I can write a second differential equation dc dt of 2 equal to d into s sf minus sf minus s, which is the state variable. So I have y2 here. We write as a y2, the second variable, minus mu into x minus mu into x is my y of one first variable. I wrote this terms divided by capital Y divided by capital Y. So I will bracket it. For second, minus 0.5 x square minus 0.5 into y of 1. Square. This is what my second terms. Now I need to write third dp by dt. So dc dt of 3 is equal to mu m, no sorry, minus dp minus d into p minus d into p plus alpha 1 into mu alpha 1 into mu plus alpha 2 plus alpha 2 multiplied by x, which is y of 1. Then, so I wrote this differential equation. I'm going to save this. I saved it. Okay. Now I know that there is a mu, so I can calculate mu because it has given me mu equal to, formula is given, mu m. So it has mu underscore m multiplied by s is my state variable, which is y2, y of 2 divided by km plus s. Km is my parameter, so km plus s, which is y2 plus k1 s square plus k k1. I have k1. I have k1. So k1 into s square. So into s is differential equations, which is second, y of 2 square. Okay, so I coded the denominator, yes, and the numerator also. So I have denominators, I have numerators, have these. So I have this term multiplied by what I need to do 1 by p minus p by p of 1 minus p by p. Third differential equations, that is y3 1 minus y of 3 divided by pf brackets this brackets and this brackets. So I have calculate um. Okay, those people who did not understood why I put y2 y3, please concentrate that the input variable here I took as a y, which has three differential equations. So y1 will indicate first differential equation, y2 will indicate second, y3 will indicate third. Wherever those parameters which is given, wherever the variables like x, s, and p will come, I will put y1, y2, y3. Here, that is the way I coded it. Then, so I right now at this point of time, according to me, I coded it. Let's run it first. So I will wait here for again 1 or 2 minutes. If you have any problems, you can ask me or you can type this on your screen.
Sir, can you once show the script file just for 3 seconds?
Script file or word file?
Script file, sir, script file. Okay, sir. Done, sir. Like, you can go back to function tab.
Okay, let's run it. Now we might get some of the errors. Let's expect it. Okay, so we got undefined variable of functions here. Not got p. Not got the p because p is a differential equation. Yeah, so I should write here y3. Fine. Okay, let's run it. I got small t. I got small y. Okay, so I got So this function was running. Let's plot this now. I can plot it basically in a subplot. So the plot 3, 1, 1 I would like to plot. Then plot so p comma y of, I need to plot all the rows first column. That's the first one. Correct. Then I will have the plot 3, 1, 2. Here is 2. There is 3. Here is 3. So look at this. The figure I wanted to show you people. So I am not aware that how much time it takes to settle. I also define the definitions of settlements. Okay. So if you look at this is the first one, the upper one looks like might be settling. Second one, it's not settling. Third one is same. So let's just increase the time horizon. Let's see how does it goes if I increase to 100. Okay, so it got settled. So if you look at the 100 second or minutes, whatever may be that, the system got pretty much settled. But we don't want to simulate it up to 100. We might going to simulate it up to 40. If you look at the 40, it's all going to settle. Okay, so we change this to 40. Okay, look at the 40. So it got almost settled. So I would also keep the 30th time. Let's see how does it goes for the 30. Okay, almost settled, I would say. See, I'm doing visual inspections, but there are methods for finding out the settling times. Okay, you can write the code for that. So, yeah, let's answer the first question. Find the steady state values and then plot the state variables with time. Give this. Okay, so we did this. This is the steady state values. So if you click here, so you will find out the steady state value of this. Yeah, so x 29.2, y value is 2.742. If we know the physics, what is first variable, what is second variable, what is third variable, we can take its name and try to understand. Second one is 1.2, third one. So I found out the steady state value. Then what it says, okay, so now I got the initial dynamics of the systems. Then I need to do a step change. Okay, and it says that give a step change in mu m. Okay, now I know that mu m is my constant at this point of time. Okay, now what happens? To provide the change in value of mu m, I need to change this code in a for loop one way. Okay, so I can say that I can simulate this for a specific time duration because I got now the last horizons 30th at the time unit of 30th is going to settle. So I can give a step change maybe at 31 or 34 seconds and still wait for 30 seconds, see how does it happens. Okay, so how do we do that? Up to this code is fine. Now I can write for I is equal to 1 to 1 to, let's say I am going to it for 100. At this point of time, I am giving my sampling time as 1 second. I need to find out the sampling time. We know how to find out the sampling time. So 30 second is my settling time. So I have time constant as 6 seconds, which is divided by 5. And 6 seconds divided by 50 is my sampling time. But at this point of time, I'm not going to go with that much. Okay. So I'm just writing it like this way. N. Okay. Now, this is T span. So T span starts from 0. So here I need to write this, I need to modify. Look at this. T0 to TF. So this will just simulate between T0 to TF. Okay. So what is T0? Here instead of T span, now in T span I'm commenting because its job is over. So I'm writing T0 T0 is equal to 0. Okay. And now I'm writing TF. Now I'm writing TF as the difference between T0 and TF is the sampling time. So what is my sampling time? So here I will use this information crudely at this point of time. Crudely. So here I am writing settling time. Because this is I know settling time is 30 unit of time. Okay. Then I have all time constants, which is settling time divided by 5. Okay, I wrote it, and then I have sampling time. Sampling time, time constants divided by 50. Okay, so these are the changes I made after I simulated initial response. Okay, let's see how much sampling time comes. So the sampling time is 0.12. Now, remember, one iteration of this is equal to proceeding in a time equal to 0.12. We can take seconds, 0.12 seconds. So for 30 seconds, how much iteration I should have? So for one iteration is 0.12. So 30 seconds I need to go. How many iterations? It's 30 divided by 0.12. If I do that one, 30 divided by 0.12, I get 250. So I need 250 iterations for initial response. Did you people understood this, what I did exactly? Or is there any questions? So first I will simulate that. So I got 250, but I will go just going to simulate for one iteration first. And I wanted to watch the T and Y. Okay, so T I got 41 by 1. T I got 41 by 1 and Y also 41 by 3. Now here is the point. The first value of these y's are equivalent to t is equal to 0, the first value in t, the last value of this y is equivalent to last value of t. So if you look at this, let's go and check what is the t1. T1 is 0. What is y? We need all the columns, 1 and all the columns. These are the values 6, 5, 95, where we started. Correct? Now, let's look at T end. It gives 0.12. Okay. Let's look at Y. We need 10. All the these are the values. So when we start next iteration of it, it should start from these values. We need to make such an arrangement there. Okay. So how do we do that? First, we will see about time. Okay. So here I came. Now my TF will become T0. So I have T0 is equal to TF. Fine. What do we mean by TF? TF equal to TF plus my sampling time. So what does this sentence means? It means that after every sampling time, I am measuring my outputs. Okay, so this I proceeded with time. Does it works? First we need to check that does it works. Okay, so I need to go it for 2 iterations and I need to put it here. Okay, now look at this. What is T0 is 0.1. What is TF is 0.24. That's why we wanted to jump by 0.12. That's what we are doing here. Okay, fine. Now come to the Y. So I have T all equal to, I'm creating it, T all, and then I need to have T end. Okay, and then similarly I have Y underscore all equal to Y underscore all, then Y, I need end values, all the rows. Does it works in that fashion the way I want it? That's what we need to check. Okay, before this we need to define this P all equal to 0. Okay, and Y underscore all equal to initial conditions, which is here I have given as x0. So I have x0. Is this clear? Because I'm starting from at a time t is equal to 0 and at a time t is equal to 0, all my state variable has value x is equal to, I mean x0 in this code, initial value. So that's what I saved it. And after in every equation, I'm saving the last values. I'm not saving the first values. Okay. So let's see, does it work the way we want it? Might be very Matlab. Bye. Let's test it. Okay. So the first 2 by 1, let's look at T all. T underscore all. So I got 0, 1.1. Let's look at Y underscore all. So 6, 5, 19.14, this is initial condition and these are the values. So it's working perfectly fine. Okay. Now let's work it for 250 iterations. Holding this. Okay. So my T all is 251 because the initial one value is there. and y all is 251 by 3. Now I need to plot this. So subplot t underscore all y underscore all t underscore all y underscore all and t underscore all and y underscore all. Then let's plot it. Let's simulate. It is an initial value, but there is something somewhere problem is creating because I'm not getting what I expected. What is the problem? You understood? I not done anything else. What I did is just simply broke the code in a for loop wise. So can anyone tell me where did I made a mistake? You can just concentrate this portion of code. Can anyone tell me where I made a mistake? Because look at the graph. This graph is not coming as earlier. Can someone point out my mistake? Maybe lota ke Aryan?
Sir, T naught is equal to TF. I think that's the mistake. Hmm.
I made a mistake. That's I know because the graph earlier and the graph here was not similar. Correct. So certainly I made a mistake. I have not done anything else. What I did earlier, I was simulated from 1 to 30 in a time span. Now I am simulating from 1 to 30, but in a for loop fashions. So what is the mistake? Karthik?
Yes, sir. I'm looking on it.
Yeah, okay. Pratish?
Just seeing, sir, like not able to recognize.
Vedant?
Trying to see that.
Okay, try to see it. Palak?
Yes, sir, the same.
Tirtha? It's a very silly mistake. Tirtha? Anyone follow? Okay. See, what the initial condition I have given here?
Sir, shouldn't the initial condition
This
change
initial
for
condition is that t is equal to 0. Agree?
Yes, sir.
Now I am simulating from t0 to tf. When t0 value is 0, that initial condition was correct. But when tf becomes t0, because here, look at this. tf becoming t0, at that time I am not updating my x0 in the for loop. Agree?
yes, sir?
Correct? So I need to update that also. How do I update that? So that I update as x0 equal to y of I need all the columns, correct? But row wise, okay. Now look at this. I am just going to so now x0 is got updated. Let's again x0 got changed. Okay, so let's plot it. Let's simulate this. Okay. Did I got the same plot as earlier? So It means that the simulations which I wrote in a for loop is okay. Okay. The better way is that top side you write simulations from 0 to n time, and then down that you can write a for loop, overlay it, and then once it overlaid, you can just comment the top portions. That's the standard practice. Now I wanted to give the step change. So 30th is fine. Now what I'm going to do is I'm going to make it 500. Okay, fine. And then after, if I is greater than 250, I is greater than 250, what I need to change? Data underscore p. Which parameter of that? Mu. 1, 2, 3, 4, 5, 6. Data p of 6 equal to what value I want. So if I know mu value here 0.48, right now I'm just hard code it, multiplied by 1.2, I can give 20%. Fine. Look at this. After 250 for loop index, I am going to get 30 seconds. So my initial dynamics will dies out. After that, in mu1, which is the sixth parameter, my data p, I am giving a step change of positive 20%. After 250, the value of data p6 will going to change by 20%, and that should observed in your graph. So let's simulate it. So earlier, when we observed this, at 30th second, it was pretty constant. But if you look at this at after 30th second, now it got disturbed. Okay, so let me zoom out the portions after 30th seconds. So it got changed. Look at this. This got 30th. It got changed. Here you might be putting. Okay, got some change. Let's do here also. Let's do some more change. That's a 50% change I have given. Again a difference. Now it's clearly visible. Look at this 38 seconds. How did I need to check this? Because I need to find out at every step. So what the step I am doing, what the intended code I wrote, is that exactly happening there? Okay, for that purpose, so I have given the step change. Now, as I have given the step change, as it got settled here, got settled here. Look at this. It might got to settle in 20 seconds. So I can just, yeah, pretty much okay for the 20 seconds. Yeah, this also. Yeah. So now from initial dynamics, I was under impression that the time constant is 30 seconds. But when I given a step change, I found out that the system is getting stable or settled in 20 seconds. So I need to recalculate that time constants, settling times, and then again run it. So initial dynamics, I can give 30 seconds always, and then step dynamics is 20 seconds. Depends on that once I can get time constant, settling times. Okay, another thing. So if you look at this, another thing, let's say second variable is your outputs, for examples. So at 30th seconds, it was 1.22, and when it gets settled, it was 0.647. I have given positive state change in my manipulated variable if I say mu m is my manipulated variable. I have given positive step change in mu m, whereas if I say my second output is my controlled variable, then I am getting negative change because the value got decreased. The final value is lower than the initial value. And here given the step change, the initial value is lower than the final value. So system showing negative steady state gain. That's the second point I got. First point I got as a settling times. Second, I got the system showing me negative steady state gain. And now if you look at this second outputs, I'm focusing on my second outputs. Look at the inflections. One here, one here, one here, one here. I might assume that system is more than first order, might be a second order, or more than second order, might be a third order. So these informations I got. Correct. Third, I did not found out any time delay, because as soon as I given the step change at 30th seconds, I am finding that output is changing at the 30th second itself. Correct. So these are the informations I found out from step change. So here I'm going to stop. We have given a step change. Now, this is what is the practice example I am taking. In last lectures, I also told you that find out the systems. So I hope that you might have found out the systems and you might have simulated your system. The same things you do on your own system, that decide the control variable, decide the manipulated variable, give a step change in your manipulated variable. Up to this, you carried out and come to the next class, which is tomorrow. Okay, so if is there any questions? Then I'm going to stop.